class. This will be our video for section 3.1, which is the start of Unit 3. 3.1 is about statements, negations, and quantifiers. Just a little background to kind of compare it to what we did with Chapter 2. And when we're dealing with sets, 2.1 and 2.2 were sort of like the definition, like groundwork for set theory and Venn diagrams. Then in 2.3 we did set operations, and then we got into like 2.3, 2.4, and 2.5 did Venn diagrams. And so 3.1 is sort of like the definition part of what we're going to do with truth tables. When we get into 3.2, that gets into the set operations. And then 3.3, which will be next week, will be the truth tables, which is sort of equivalent to dealing with the Venn diagrams. And so the nice thing about 3.1, like the number of definitions we have to learn is much smaller than we had to do with set theory. So, and another thing that's sort of good and bad is that a lot of the definitions in dealing with logic and truth tables is related to what we did with set theory and Venn diagrams, but that can also cause confusion as well. So if you figured out for Chapter 2 how to successfully deal with the definitions and the symbols and all that, then you're set up well for Chapter 3. I will say that even though there's not as many definitions, it's more important to pay attention to the small details with what we're doing in Chapter 3. Okay, because there are going to be times where it may seem like we may have a couple of right answers, and you kind of have to pick the best right answer with some of these definition questions. So, but overall, this is similar to what we had to do with Chapter 2. You have to learn your definitions, you have to learn your symbols, and you have to apply them. Okay, but now we're going to be doing it with truth tables over the next couple of assignments. All right, so in Blackboard, what I will be working from is I've moved the resource folder for Unit 3 up towards the top to make it a little bit quicker to access. In that folder, one thing I've done a little bit different based on the feedback I got from Chapter 2 when I made that document called the definitions one place. People seem to like that. So I made another definition style handout. I don't have the 3.3 in there yet. That's coming, but it's more, this handout is more of the definitions, the big picture sort of stuff, and then that leaves the lecture examples that will be more specifically towards like homework examples. So that way I kind of separate them out a little bit. So we have one document for the definitions that you can kind of reference as we're going through this, and then one document for the examples. All right, so speaking of, let's get into the notes. We'll bring up the document camera and we'll get going. All right, so I am starting with the definition. So that's, might do one or two examples, but the 3.1, it's like I said, there's really only three sort of definitions or ideas we need to talk about. One thing I do want to point out is since we're still doing logic, which is rated Chapter 2, I don't know how many of you ever had to take French and Spanish. That's it. When I was in high school, I'd take 3 years of language. My first 2 years were French, my third year was Spanish. And so when I was first learning Spanish, I was like, oh, hey, all my French stuff that helps because a lot of the words are similar and sort of stuff. But as I got deeper into Spanish, then it started to be confusing. Like, am I remembering my Spanish? Am I remembering my French? And I kind of think that these topics are kind of related between Chapter 2 and Chapter 3. Okay, so we are learning. Think of this again as a new language. You learn the set theory language in Chapter 2. Now you need to learn the logic truth table language in Chapter 3. Okay, but as you'll see, there's some definite overlaps. So like the core idea of what we need to do, we learned in Chapter 2. Now we're going to expand upon it. Okay, so 3.1, what are we talking about? We have statements, negations, and quantified statements. Okay, so what is a statement? Okay, so a statement is a sentence that's either true or false, but not both simultaneously. Okay, and so one thing about that simultaneously, what does that mean? Not both simultaneously. So a statement has to be true or false, one or the other. If it's both, that often it's like if you say that something related to opinions, like if I said fall is the best season of the year. Well, some people are going to think that's true. Some people are going to think that's false. And so that means it's both at the same time. So fall is the best season of the year is not a statement um, in terms of logic. It may be an English statement because it's a sentence, but it's not a logic statement. Okay, so this is where we got to separate the math and the logic language versus the English language. Okay. And whether or not it's true, that really doesn't come into play until we get into 3.3 and start dealing with truth tables, and we'll kind of deal with those consequences. But statements can be false, and that's fine. They're still a mathematical statement. So if I said February is a fall month, that's clearly false because it's a winter month, but it's still a mathematical statement because it is false. Okay. Couple of things with the notation. When we are dealing with our statements, P, Q, R, and S, lowercase and italics is the letters we typically use. If you see like capital A, capital B, that's often like elements or parts of a statement or parts of a sentence, but the sentence overall is P, Q, R, S. Those are the most common letters. All right. And so let me do these three definitions and then we'll do some examples. Okay. So the next main definition from 3.1 is negating statements. And so since a statement is either true or false, negating kind of works like it sounds like. So the negation of a true statement is a false statement. Negation of a false statement is a true statement. Okay. It is kind of that straightforward at the beginning. Right? The symbol for notation. Now this is a little, in set theory, like the closest to negating statements was complement. With complement, you had the apostrophe, which was often overlooked. For negation, we have that tilde, or cursive tilde, if that's what you want to call it. If you look on your keyboard, it's in the upper left. You have to hit shift to be able to type it in. But that is the negation of P, and just like with complement, we'll call it not P often. When you think of negation, you may think of opposite of. So it kind of works like integers, opposite of a negative is positive and vice versa. So that's opposite of true is false and vice versa. I will say this though, when we're dealing with quantifiers, which we'll get to next, it can get a little bit more complicated. But the basic idea of negation is we're trying to make a true statement false or vice versa. All right, and then quantified statements. Well, the root word to quantify, I think it was quantity, but you're dealing with amount of things. And so our typical quantifiers are all, some, and none or no. Okay, so some of these statements will be dealing with all, like all elements in a set sort of thing, or we might be just dealing with some of them or with none of them. And this is where paying attention to the details, even more so than unit chapter 2, becomes important. There are, especially when we're translating this from English. So we go to page 2. So like there's equivalent ways to say things, and this is where it gets tricky sometimes. So if you want to say all A are B, it would be cool to say there are no A that are not B. So there's sort of a double negative there. And in English, we have double negative, you end up back where you started. So it kind of works logic-wise as well. So something equivalent to some A or B, there exists at least one. So there exists at least one is equivalent to some. No A are B. Another way to say that is all A are not B. Okay. And then some A are not B, not all A are B. So this is where, again, I think you start to see where, like you don't like true or false because they can feel kind of tricky. Unfortunately, this is sort of the language that happens. So with that. Right. So now before we get into negating quantified statements, which can be a little tricky, let's look at some basic examples from the homework. So I'm now going to go over to the lecture example handout. All right. So let's see. No, I'll wait on that. Okay. So let's just start with 2 through 5. Determine if the following sentences are statements. Okay. So number 2, no professional basketball player has ever gone on to become a news announcer. Okay. So is that a statement that's either true or false? Okay. Well, that's something that's sort of like verifiable, that it's not an opinion. Um, and I'm pretty sure there are, I know of at least a handful of basketball players that have become news announcers. So that is a false statement, but it's something that we can know for sure if it's true or false. So yes, this is a statement. Number 3, 3 plus 9 equals 10. So our statements don't have to be English sentences. They can be mathematical expressions, equations, or inequalities. Those can definitely be potential statements. Now, is 3 plus 9 equal to 10? No. So it's false, but it's still a statement because it's either false or true. It can't be both. So how about 3 or 4? Do you like this color? Is that a statement? Well, first of all, it's a question, not a statement, right? So it's not even in English. It's not going to say that's a statement. Plus, when you like it, that's like a yes or no question, not a true or false, which can be different. So that puts it more into the opinion range. But the main thing is, since that's a question, that is definitely not a statement. And then number 5, this test is too hard. Is that a true or false statement? Well, if it depends on like who you're asking and which test you're talking about, which course you're talking about, that's more of an opinion. So that some people might say true, some people might say false. All right, so since it could be both at the same time, then that is definitely not a statement. That's sort of the different, so when we talk about mathematical statements, we're not talking about English statements, which is just pretty much any sentence. Mathematical statements have to be either true or false. We don't care which one, but it can only be one of the two, not both. Yeah, so those are statements. All right. One thing I will say is, particularly when we get into 3.2 and 3.3, we're going to have to be translating a lot of English to symbols and vice versa. And so one of the things I would definitely get in the habit of is clearly identify your letter and your statement. So like if our statement is today is a weekday, then say like P equals. Get in the habit of writing that out. Or like Q and then the colon 4 is greater than 5. Something like this that clearly identifies like which statement with which letter. That will make your like translations from English to symbols a little bit more straightforward. All right, negations. Okay. So for negations, true becomes false and vice versa. Okay. And so form the negation of the statement. Now, one thing that's missing, there's a tilde that we're talking about P, so that should be tilde P. Okay. So today is June 19th. What's the negation of that? There's multiple ways you could say that. The quickest is today is not June 19th. So if you don't have the quantifiers of the all, the some, or none, you can use not. That's a very easy way to negate a statement. So like 9, Q, Copenhagen is not the capital of Brazil. So if we want to do the negation of Q, so tilde Q, well, what's the negation of Copenhagen is not the capital? Well, Copenhagen is the capital. Okay, so in this case, the statement starts as a not statement. And so to negate it, we basically take the not out. Okay. I think that's relatively straightforward. Again, it's once we, until we get to the quantifiers, we don't get too messy. All right. How about 11 through 14? Let P, Q, and R represent the following statements. P1 plays hard, Q1 is a guitar player, R, the commute is to work is not long, and S, it is not true that the car is working. So express the following statement symbolically. So one of the things you have to do is, first of all, which letter are we talking about, and then put it in symbol form. So the commute to work is long, so that is dealing with R. So this says the commute is long, this says the commute is not long. So we're doing the opposite of not long because we took the not out. This would be not R, or the negation of R. 12, the car is working. S is the car. It is not true that the car is working. So we took out the is not true. So we're left with just the opposite of that. So that would be tilde S. So 13, one does not play hard. Well, P is one plays hard. So now we're saying one does not play hard. So that's the opposite of P, the negation of P. And then 14 is express tilde Q, or not Q in words. Q is one is a guitar player. So if we want the opposite of that, or the negation of that, we say one is not a guitar player. So again, basic negations are pretty straightforward. All right, now we're getting into a little bit of the mess. And so we deal with quantifiers. So again, remember, basic quantifiers are all, some, or no, or none. When we get to English, there's a lot of different ways we could say that, and this is where it can really get kind of tricky. And we got to find the equivalent statements. And one thing in the Math Lab homework, if they're asking you for an English statement, it will be a multiple choice problem. So basically, you got to pick the best answer out of multiple choice. If they want it in symbol form, then you're going to have to put the symbols in. Okay, so let's start with some English versions of this. So express the quantified statement in an equivalent way, i.e. that in a way that has the exact same meaning. So let's start with this. All mathematicians are humans. Okay. I guess that means we're not talking about dolphins or anything like that, or AI. So all mathematicians are human. Sometimes it's multiple choice. Let's just kind of go through the list. Okay. So the first one is there are no mathematicians that are not human. Well, that sounds like the opposite of what we're saying. So definitely not that. All humans are not mathematicians. Oh, wait a minute. We'll go back to one. There are no mathematicians that are not human. I was only reading one of the no's there. All right. So that's a double negative. So that's a possibility. So let's come back to A. Okay. See, I've been doing this for a while and I still make mistakes with this. So you got to be very careful here. So all humans are not mathematicians. So this is two things. One, order matters. So it starts with mathematicians and then talks about humans. We kind of want to keep that order. So this one starts with humans and then all humans are not mathematicians. Well, I'm really concerned about mathematicians being human. The fact that all humans are not mathematicians doesn't tell me anything about all mathematicians. So that one, not necessarily, you can't prove it right or wrong. It's talking about humans, not mathematicians. So some humans are not mathematicians. So that kind of, again, we're talking about humans here, but we really need to be focused on mathematicians. So I'm going to cross that one out. So at least one mathematician is a human. So which one is better, D or A that I initially crossed out? Because I missed the fact that there were two negations. So at least one mathematician is human versus all mathematicians are human, versus this one says no mathematicians are not humans. Okay. So this one only tells me one or more. This one tells me that they can't be a mathematician if they're not human. Okay. So that one I mistakenly crossed out at the beginning because I was reading it too quick. It's actually the right answer. Okay. So this one might seem okay, but there's no guarantee that all of them are. We know that some of them are, but it needs to be all. So that all is the different why D is not the right answer. Okay. So some mammals are cats. So let's go through the choices. Well, this one talks about cats first. So I'm gonna not want that one. So no mammals are cats. So is that the same as some mammals are cats? No, that's there has to be some, and it can't be none. So it's definitely not B. There exists at least one cat that is a mammal. Okay. Well, that sounds like maybe, but again, this one is starting with cats, and we were focusing on mammals. Okay, so let's look at the next one. At least one mammal is a cat. Is that the same as some mammals are cats? Yes. Okay. So C may or may not be sort of okay, but D is a much better answer because it's focusing on mammals, whereas C is focusing on cats, because cats comes first. All right, so how about 18? So some drinks are not liquids. A, some liquids are not drinks. Well, again, order matters. So I don't even really want to look at A because it's the order is backwards. All drinks are not liquids. So some drinks are not liquids. This one says all drinks. So because of that, I'm very hesitant on B. Not all drinks are liquids. So this is some. This is not all. And drinks are liquid. So I'm going with C. And then all drinks are, that one's definitely not it. So C. So instead of saying some drinks are not liquids, we're saying not all drinks. That's definitely better than B, which was our only other choice. All right, 19. No politicians have told a lie. Okay. No political commentary other than to say then we know this is a false statement, but it's still a statement. Okay. So no politicians have told a lie. So this one is no. This one says some. And so that definitely doesn't work. That because we want the meaning the same. So all politicians have told a lie. That's sort of like the exact opposite, feels like. It may not be the exact opposite, but it feels like it. All politicians have not told a lie. Okay. That one sounds promising. We'll come back to that. And then at least one politician has told a lie. That one says no politicians, so it can't be that. So all politicians have not told a lie. That means the same as no politicians have told a lie. So this is where you have to pay attention to details. Okay, so that is quantifiers without negation. Now let's talk about quantifiers with negation. Before we get into the example, I want to jump back to the handout, the definition handout. So how do you negate quantified statements? And this is, I would say, definitely the trickiest part of 3.1, maybe even for the whole chapter. Okay, so before we talk about this, let me give you an example. Is all math students or all students in this class like math? So is that a true statement or a false statement? I would love for that to be true. I'm pretty sure we're in agreement that's false. But why is it false? Does that mean that everybody, so I say all students in the class like math, does that mean it could be false and nobody can like it? No, it's false if at least one student does not like math. Does not like math. So when we say at least one, that's equivalent to some. So to negate an all statement, all we need is one person to make it false. So that's where you have to be kind of careful with true and false in math. If I have a statement that's true 99 times out of 100, that's still false because of that one time it's false. And then so, all A or B is negated as some A or B. So an all statement is negated, or the opposite of that is some. Now, for starting with some, so like I said, some students, if I said some students in this class like math, what would be the opposite of that? Well, the opposite of some, there'd have to be nobody that likes math. The some says there might be one or two people that like math. So if that's true, to be false, like I said, had to be nobody. So the negation of some is no. So that's where you kind of have to be careful. The negation of all is not none. And the negation of all is some, and basically vice versa. Again, so like I said, it kind of goes back to how we think of, but what math thinks of true and false is it only takes one to be false. So that's why it's some. It's negation. Okay. And I had an example, but I kind of like this example better. Okay. So okay. So let's look at the examples. All right, write the negation of the quantified statement. And then the negation should begin with all, some, or no. Now in MATLAB, which I'll bring these up, again, we're talking about 20 and 21 in English. So this will be a multiple choice problem, but let's do it without multiple choice. Okay. So all weeds are plants. So how do we negate that? Well, we said the negation of all is some. We could say, so what if you said some weeds are plants? Is that the negation of that? Because I'm talking all weeds and I'm going to some. So here's where you have to be careful. Because if you say some weeds are plants, it sort of that may sound like it implies that some are not, but we didn't explicitly say that. And so then you're making an assumption, and you don't like to make an assumption. You want to be very precise in the language. So it would be better say this. So some weeds are not plants. Okay, so what that does is that takes the input, the guesswork out of it. I'm not implying that some weeds might not be plants. I am specifically saying some weeds are not plants. And if some are not plants, then they can't all be plants. All right, so this is definitely the much better way mathematically. In the English, you might get away with saying that that's the negation, but this is a math class, not an English class. This is where like paying attention to those details are important. All right, how do we negate some mammals or horses? Well, some is negated by no. So say no mammals. Does that one? Yeah, so this is a little bit more straightforward than they all, because if some mammals are horses, that means now I'm saying can't be any mammals that are horses. So that one's pretty straightforward. Again, this will be multiple choice, and I'll bring up math up to show you. Okay, so that is an English form. Let's do this. Let's look at some other way. So P, everyone is asleep. So now we want not P. So we could say everyone is not asleep. That might be one way. How else could we say that? How about someone is awake? I think both of those would work. Because in this one we're going directly to, I kind of like the second one a little bit better. Because the opposite of asleep is awake. And now we're saying, instead of saying everyone is asleep, now we're going to the opposite. This is kind of like the not plants one. This one might be okay. Someone is awake, I think, is a stronger negation. All right, and then P, some athletes are musicians. So what would be the negation of that? All right, so some is negated by no. So all you do is say no athletes are musicians. Now, again, whether or not this is true or false, we don't really care. We just know we want the opposite. So if that's true, that some athletes are magicians, this would be false. If that is false, then this would be true. So it doesn't matter which one's true or false as long as one is one way and the second statement is the other way. Okay. Let me bring MathLab and do a couple more of these. I'm going to show you how the multiple choice works. Okay. So in MathLab, oh, by the way, so we're starting Unit 3. There's a lot to scroll through. One of the things you can do is up here at the top. Notice it has this all chapters. We are now in Chapter 3. So if you want, you can come up here and just select Chapter 3 Logic. And what it does is it jumps down. Now it doesn't have the Chapter 4. You have to change that, but that'd be a quick way to get down to the Chapter 3 stuff. All right, so let's look at some of these. Share the right screen. Okay. So the statement no A or B can be expressed equivalently as, so no A or B. I want equivocally means we want, or equivalently, yeah, we want the same. So no A or B. There are no A's that are not B. That tells me all A are B. That's not what we want. All A are not B. So that means no A are B. There we go. If there's at least one, then that's not none. Okay. All right. Let's jump to. Okay. So what is the negation of some A or B? Some A or B, but not all A or B. Hmm. Well, we know. Okay. So that almost kind of sounds the same. Let's see if we have better. So no A or B. That one sounds, so instead of having like one or two that might be B, we're saying none. How about C? Not all B are A. C and D, when I look at them, I kind of, in my brain, I'm already saying they can't be those because our statement starts with A, goes to B. So A is what we're really focusing on, whereas C and D, since they're starting with B, they're focusing on B. All right, so they're basically going backwards. We don't want to go backwards. We need to go A to B. Right? So the negation of some A or B is no A or B. Right. Express the quantified statement in an equivalent way, and then write the negation. Right? Negations start with all, some, or no. All right, so some bushes are not silver. So we want, first of all, we want the equivalent to some bushes are silver. So when I hear some, I kind of jump to at least one, but let's see if any of the rest of them. It can't be A because some, this says all, which is definitely not some. So not all bushes are silver. Maybe. There are no bushes that are not silver. Well, if there are no bushes that are not silver, that means all bushes are. Okay. It doesn't say all bushes, it says some. So is it B or is it C? So here's the problem with B. So not all bushes are silver. Um, and it sort of implies that some are. Or let's see, so some bushes are not silver, not bushes are silver. Okay. Oh, yeah. So this is where that not comes into play. Which one's better, either B or C? Okay. So some bushes are not silver, so not all bushes are silver. That one sounds to me like we're good to go. So, like I said, I don't do truth tables near as much as I do the set theory and Venn diagram, so sometimes it's a little hard for me too. Usually I can get it down to 50-50, and then you just gotta try to make sure that you're getting the best answer out of it. All right, so which is the negation of that state? So some bushes are not silver, so now we want no bushes. Let's see. So some are not. So we want to be the opposite of some would be zero are not silver. So not all, some, no bushes. Oh, oh, did I just do the like I said, A when I'm okay. So let me slow down. So some bushes are not silver. It's that not that's kind of throwing me off. So not all bushes. Some bushes are not silver. All bushes. Okay, so I think what's happening here. Let me check this. Okay, so the not in the original statement threw me off because I was trying to do it without the not. But if some bushes are not silver, so that means opposite. So instead of saying no because of that not, I'm going to say all, but then take out the not. Does that I hope that makes sense? Because now this is sort of like a double negation. So all bushes are silver says that there can't be any that are not silver. I don't know if I'm explaining that very well. This is where it gets tricky. So that when you start with a not, it almost sometimes might be easier to take out the not in the original statement, negate it, and then you know negate the second one. Let's do another example. All right, see if I can explain this a little better. So no plane can fly faster than 400 miles per hour. Okay, so the following statement is false. Use representation of P to express P in words. Okay, so we want the negation of no plane can fly faster than 400 miles per hour. So my first instinct is no is negated by some. So this is so some planes can fly faster than 400 miles per hour as opposed to no plane. So D might work on first glance. So some planes cannot fly faster. That sort of implies that some can, but this one specifically says some can. That's why I'd go with A. So now, what can you conclude about the resulting verbal statement? So they're talking about the verbal statement is the not P. Well, if P was false, then not P has to be true. It can't be true and false simultaneously because then it's not a statement. If it's only partially true, that means it's partially false. So A and B are saying the same basic thing. Neither of those can be true if it's a statement, right? But original statement was false, so the negation has to be true. Okay. City council in large northern metropolis promises citizens that have been to snow, all major roads connecting the city remain open. But the city council did not keep its promise, right? A statement that represents the situation. Okay. So they were saying that all major roads connected to the city would remain open. They did not keep that promise. Okay. Basically, all major roads connected to the city would remain open. We need to negate that. That is what this is saying because they didn't keep that promise. So the negation of all is some. So instead of all major roads being having shelters open, we're going to say no major roads was not open. At least one major. So we don't know that all of that they were closed. So that's sort of implying at least one major road connected to the city to its shelters was open. Now that means it could be more than one. It could also be all. So again, that's a bit ambiguous. So at least one major road was not open. Okay, so opposite of all is some. So that at least one is some. And then no major roads. Well, all and no are like polar opposites. All right. But that's like two sides of the coin. But we need to negate that. So still C is the best. Is the opposite of all is going to be some. Okay. So this is where, like I said, even sometimes my explanations on some of these for the quantifiers, it's I can find the right answer. I can't always explain exactly why. I get down to like one or two, and this just takes practice. And I'll admit that I don't practice this near as much as I do the set theory and Venn diagrams. Um, but hopefully you can see that it's like the sort of detail you have to look for. Um, and I think we were fine until we negated quantified statements. So that's where it's going to be a little bit tricky, and you just got to spend a little bit more time with that, and just you have to learn to get those details and watch out for double negatives and all that sort of stuff. All right. Well, that is all I have for 3.1. And the next video is going to be 3.2 with compound statements. And I will get that out today as well at some point. Have a good day.